This is the first video for section 6.6, and it will discuss solving systems of linear equations using determinants, and specifically focus on determinants of two linear equations. The next video will discuss how you can solve a system of three linear equations. So just a reminder of what a system of linear equations is. It means you have some coefficient times x plus some coefficient times y is equal to some number, and that you have two such equations where a, b, and c are different numbers. There are multiple ways of solving these equations. One way is known as Cramer's rule. And Cramer's rule says that if we take the coefficients on the x and y terms and put those as a determinant in our denominator, and then replace whichever coefficients correspond to the letter we're looking for, so in this case we're looking for x, we replace the a's with the c's, and in the case of y, we replace the second column with the c's, then we can end up with a solution for x and y for this system of equations. Now, some things to keep in mind. The system is inconsistent if the denominator determinant is 0, but the numerator is not. And this means that you have parallel lines, there's no solution. A system is consistent and dependent if both the numerator and the denominator determinants are 0. So if it is consistent and dependent, this means that they are the same line, and in this case you have an infinite number of solutions. And it is consistent and independent, which is typically what we want, if the denominator is not 0. And so this would give us the one solution that we typically want with a system of equations. So let's try some examples. So for this first example, it's usually easy to find the determinant of the denominator since it's going to be used for both pieces. And if it's 0, then we know that we've got either a system that is going to produce no solution or infinite solutions. So first things first, let's look at the determinant of 8, -3, 5, -7. So that's the denominator for both of these. So we would end up with 8 times -7 minus 5 times -3. So we end up with -56 plus 15, which is -41. So we're not 0, so we know we've got a consistent and independent system, which is going to produce one answer. So now let's look at finding x and y. X is now going to have the numerator. We're going to replace this first column with our answer. So -43, -73. We keep the second column, -3, -7. Again, we replace the coefficients from x with the constants given. So in this case, we have -43 times -7 minus -73 times -3. And you should end up with 82. So that's your numerator. Your denominator we found was -41. And if you divide 82 by -41, you end up with -2. Now for y, we are going to replace the second column. So the first starts off, we're going to stay the same as the original, which was 8, 5. We replace the second column with -43, -73. And again, our denominator is -41. So in this case, our determinant ends up being 8 times -73 minus 5 times -43. Again, all over -41, our denominator. And in this case, we end up with -369 divided by -41, and this comes out to be a +9. So our solution to the system of equations is that x equals -2, y equals 9, or you can write this as the ordered pair, -2, 9. Now, I want you to pause the video at this point and try example 16. So, in this case, you should have been a little wary at first when you found out the denominator was 0, but you still have to go through the next step to figure out if the numerator is also 0 to determine if it's no solution or infinite solutions. In this case, the numerator is not 0, but the denominator is, and this is undefined, which leads to an inconsistent solution, and there is no solution to this system of equations. One last example that will work together, and this one involves variables throughout the entire example. So I'm going to go straight to solving for x and y because we're going to have the a and b in there. We're never going to have actual just numbers. It is still easier to set up the denominator first, so 5, 2, a, negative b, because again, we're going to be replacing the first column with our BA, and then we're going to leave the second column alone, A, negative B. And I'm going to just set up y here. Again, we're going to have the same denominator, 5, 2, A, negative B. And in this case, though, we're going to replace the second column with the BA, and we're going to keep the first the same. So, if we go through, the determinant of the numerator of x is going to be negative b squared minus a squared over negative 5b minus 2a. And the only thing we can really do to simplify is to pull out a negative from everything. So if we pull out a negative, we end up with b squared plus a squared up top. And if we pull out a negative in the denominator, we're left with 5b 2a, and negative divided by negative would give you positive, so you're just left with b squared or a squared divided by 5b plus 2a. Again, everything ends up being positive because we pulled negatives out of all of those. If we look at y, we are going to have 5a minus 2b. That looks kind of similar. And in the denominator, we're going to have negative 5b minus 2a. And unfortunately, in this case, we do not have anything that's going to be able to simplify because this is a 5a and this is a 5b and 2b and 2a. So they have different variables, and so we can't simplify any further. So this concludes the first video for section 6.6. The next video will look at systems of 3x3 equations and applications.